Oh,
Yes.
Can you just check the online setup if the microphone is off? You're not muted during the break. Okay.
okay, we can start. Hello, everyone. Welcome back after a short lunch break. In this session, we have 4 presentations. My name is Jad Abu Hamid. I'm a doctoral researcher at Tampere University in Finland, and my co-chair.
Lovisa Lundholm from Stockholm University.
Okay, so our first presentation is by Kim Sinhan from GSI in Germany, and she's going to talk about effectiveness of low energetic alpha particles, the importance of the radiation sensitive targets.
Thank you very much. Okay, so just to give a short background, I'm in the second year of my PhD, and I'm predicting the effectiveness of alpha particles using a mathematical model. But don't worry, I will not show any equations, only one. So let's recap. What's the main difference between photon radiation that we have from the sun, for example, and charged particles like alpha particles that can be produced when breathing in radon? So for alpha particles or ions in general, you have, oh, the pointer's not really working. Sorry, can you see it now? I will use this. Does this work? Can you see the pointer? Okay, perfect. So because of the high mass, the particles are hardly deflected from their primary particle track. And because of the charge, you have this really dense ionization pattern around the primary track. And that's why when you look at the dose distribution, you get these really high dose peaks. So this box is in the dimension of a cell nucleus, so in the range of micrometers. And wherever an alpha particle traversed the cell, there you can see this kind of peak. And for photons, on the other hand, or in general, sparsely ionizing radiation, they are called like this because they make much less ionizations in the same space. So here you can see the same cell nucleus, and they receive the same macroscopic dose of 2 gray in this example to the nucleus. But for the photons, the dose is distributed homogeneously. And for ions, you have this very heterogeneous dose distribution. And the DNA is generally considered as the radiation-sensitive target because ionizations to the DNA are the main cause for cell death after irradiation. And when you have densely ionizing radiation, then you can induce much more complex damages to the DNA than in comparison with photons, where you only have these sparse ionizations. And the point is that in general, we have a sophisticated DNA repair system that even ensures our survival. So our cells are repairing damages all the time. But the point with alpha particles is just when it gets so complex, these damages, then it gets difficult to repair. And that's why for the same physical dose, you have a higher biological effect, which we quantify in terms of RBE. So it means the physical dose that is needed for photons to achieve the same effect as for ions. So if you have a RBE for 2, for example, that means that alpha particles would be twice more effective. And it's something like the radiation weighting factors that you are used to in radiation protection, I think. And a biophysical model that's capable of predicting the RBE is the local effect model, LEM, that was initially developed at GSI. And you can imagine it as a kind of black box model. So we don't consider all the complicated biological processes that are going on in the cell, but rather we derive the effect using the cell's response to photon radiation as an input. So we have these kind of dose response curves that a lot of you have probably already seen that are often quantified according to the LQ model. So in terms of alpha, which represents the slope of the survival curve, and beta, which characterizes the curvature. And then we give this as an input. Here we have the endpoint cell survival, but it can also be mutation load, for example. And then we also need some physical information about the considered radiation type. So the energy and the LET. And instead of all these discrete ionizations that I showed in the beginning, we use a continuous representation. So whenever you see these kind of figures, then I am showing particle tracks. And exactly with that, we try to predict the cell's response to ion irradiation based on the response to photon irradiation. And that might seem a little counterintuitive at first, because the whole point is that alpha particles are different. So I will try to explain the basic idea of the local effect model, which also gives it its name, because when you look locally, so you zoom in very much, then you can approximate this spike distribution to be homogeneous again. So when you remember the photon distribution that I was showing in the beginning, that's how then you can get this link. If we know how the cells respond to photon radiation, then locally we can link the ion world to the photon world. And so what I did is, because the LEM was initially developed in the context of radiation therapy, where we have high energetic ions that usually don't lose a lot of energy within one single cell, but for alpha particles that are produced during the radioactive decay, they only have a range of a few cells usually, and so they can lose a significant amount of energy within a single cell, which had to be considered in our model. And also a lot of physical parameters here. For example, you see these ion tracks, and how large the ion track expansions are, so how far the liberated electrons can travel, also depends on the energy of the primary particles. So when you have low energies, these ion track expansions become small, and it also changes along the way. And this will also be important for later. But I implemented this, and then it's always important to test models against experimental data. So at GSI, there was the particle irradiation data ensemble that was developed, and I expanded this database with alpha particle experiments that weren't included before because of the low energies. And the problem was that we just couldn't predict the experimental data well with the model. So we were questioning a lot of assumptions, because for high energies, the LEM was always doing a good job in predicting the effectiveness. And at some point, we thought about the relevance of the target, which initially in the LEM, we consider the cell nucleus to be the radiation-sensitive target because it contains the DNA. And as a first approximation, we had that it is distributed homogeneously, but I will come back to that later. So now, when you are in the limit of low energies, as I said, then the ion track expansions are very small, and the LET, and so the ionization density within the tracks is very high. For alpha particles, you already know that, but you can go to even heavier ions with higher charges to have even higher LET. And then every time you hit the cell, it should lead to an activation because of this high LET. And every time you don't hit a cell, that's the only case when it's not inactivated. And that's why when you measure an activation cross sections, so maybe this was a little confusing for non-physicists, cross sections you can imagine as a kind of effective area in which an interaction between the target, so in this case the cell nucleus, and the incoming particle can take place. And so in this limit, when you have very high ionization densities, when every time you hit the target, it's inactivated, then this should correspond to the area of the target. But what you see in the experiments is that you have this convergence for low energies, independent of the ion species. For high LET, you converge towards these low inactivation cross-section, but it's not the nuclear area that you're converging towards. It's much, much lower than the nuclear area. So that means that there are cases, even though the particles have very high LET, the cell isn't killed. And so this means that not the whole cell nucleus can actually be the radiation-sensitive target, because we see that in 60% of the cases, you shoot through and nothing happens. And so that's why for the low energy, it becomes important to consider the target structure. This wasn't a problem before, because if you consider now that within the cell nucleus, you have some inhomogeneities, and then you have high energies that we're usually considering, you have large ion tracks, so you cannot really resolve these inhomogenities. But now when you're going to low energies, so in the case of alpha particles, as I said, we have these small ion tracks, and then it can happen that you can shoot through the cell nucleus without hitting any DNA or just insensitive areas. And that's what I had to implement in the model. This was a little bit complicated, so I will spare you with the details, but here now the comparison against the experimental data. So we developed kind of a new model version. It's called low energy adaptation of the LEM, short LEA, which you can see now here in yellow. And blue is the experimental data of the PIDE database. And red was what we had before. So before we really couldn't predict the data, and now it is in good agreement. So that the model is finally ready. We started collaborating within other partners than Radionorm. And so one collaboration is with Szabolcs and Balázs. Szabolcs will give a presentation right after me, so he will explain his model in more detail, but they developed a model for hyperradio sensitivity based on the principle of minimizing the mutation load, and they're looking at this for photon radiation. So they provided us with a mutation yield for photons, and we can predict the mutation yield after alpha particles then to then in the end hopefully be able to explain why for alphas a lot of times you don't see hyper radio sensitivity, on which cases you do see it. So yeah, the main point of our model is always when we have input from the photon world, then we can predict for alpha particles. And we're also trying to find a collaboration with Jan Bui. We've been discussing about this yesterday. He has a sophisticated model that's mimicking the bronchial epithelium, and this would be much better than the cell survival experiments we usually have, but it's just more complicated since it is more complex to find suitable endpoints there. But yeah, the final thing, how am I doing with time? Okay, so I have time. So the final endpoint that would probably also be most interesting for the Radionorm project that we want to look at is then going toward carcinogenic endpoints. And this also might not be clear how we can do it with the LEM, because I said, okay, we use it to predict cell survival. We can also predict mutation yields. And now the point is that these are actually kind of competing processes. So maybe intuitively first you would think higher doses are more dangerous, but when you, so blue is the survival as a function of the dose. When you have high doses, you have a high, and the orange one is the mutation load. You have a high number of mutations, but most of the cells are killed. So the idea is that you need that a cell needs to survive to be able to carry on mutations, and so we can use the LEM once to simulate the cells that survived, and then use it a second time to simulate the mutation yield to then get some kind of measure for the neoplastic cell transformation. So how high the probability is that a cell will survive and carry on a mutation. Yeah, and that was it. And with that, we would like to use that to estimate the risks of these dose hotspots that other people within the work package 3 are investigating. Yeah, and if anyone is interested in anything else that we can provide predictions for, feel free to approach me. I would be happy for any other collaboration. With that, I would like to thank you and my group from GSI, and especially the ECRs from Radionorm.
Thank you, Kim, for the interesting presentation. Any questions from the audience or online?
Thank you for the interesting presentation. You mentioned that the inactivation cross-section of the nucleus was much smaller than the actual size of the nucleus, but can you relate that cross-section to the size of biological structures within the nucleus, or do you have any information about that?
Well, the point is it's not so easy, because what we are seeing, the cross-section is kind of like a projection, right? So when we're going through the cell nucleus, and maybe we have some DNA here and DNA here, then we cannot resolve it like in 3D, but we can only see the cross the projection, and so this is around 40% of the size of the nuclear area, and so this corresponds something to like 5% of DNA or like sensitive area within the cell nucleus, which doesn't seem a lot. I don't know if are you a biologist? Okay. Yeah, but I mean, we also know that the DNA actually doesn't take up a lot of the volume in the cell nucleus, and so yeah, we are still also talking to biologists to try to find some evidence for this.
Thank you.
We have a question online from Fredo.
Yes, thank you. Thank you for an interesting presentation. If I understood correctly, your endpoint at the moment is cell survival, right? And the
Yes.
RBE that you come up with is something like 2, 2.5, 3, which is interesting and is similar, well, up to 5 maybe, yeah. But what I wanted to ask is that in the case of neutrons, you also have usually RBEs of 2 to 4 for cell survival experiments, but when you go to mutation or transformation, it can easily be 10, 20, or cancer induction in certain experimental systems up to 100. So would you expect something similar to happen here, that you cannot easily translate the cell survival RBEs to mutation or transformation RBEs?
Yes, I think you cannot transform that easily. So first of all, I want to say that when you go to lower energies, the RBE here would go even higher. It is just cut off because the experiments, they usually stop at some energies where the particles still almost go through the cell, but we don't have experimental data for lower energies, but the simulations show that the RBE would go higher. And that is just one point I wanted to mention. But to your question regarding the RBE for different endpoints, so we don't really make an assumption from the RBE for cell survival and then go to the RBE for mutation yield, because the RBE for the mutation yield we simulate separately. We just don't have a database to compare it with yet, but I think in principle this RBE would be higher, yes, because in cell survival you always have some kind of limit by the overkill effect. So when the cell is dead, it can not be more than dead. That's why you have this limit, and for mutation you can always have more mutations. So RBE mutation yield I think would be higher, but RBE carcinogenic endpoints, I don't know which range it will be in yet.
Thank you. Very important, because I mean, we always assume quality factor or radiation weighting factor of 20. So that's a bit away from your 2 to 5. So we have to understand that. But yeah, there's still some work to do, I guess. Yeah. Thank you.
Thank you.
Thank you for the nice presentation. I also have a question regarding the RBE, because the RBE is very dependent on what kind of biological endpoint you're looking at. And some endpoints are really very nicely to be resolvable, but some endpoints not. So if you look, or the RBE and the weighting factors mainly rely on dicentric induction, because with dicentric induction you can really resolve different radiation qualities, photon qualities, and therefore sometimes when you're using these endpoints, you will get perhaps other RBE values than if you were regarding other endpoints like cellular survival.
Okay, so can you repeat that endpoint again? Because actually I haven't looked at it. Dicentric induction, you said?
Dicentric chromosomes, because
yeah,
something very special for ionizing radiation because of the double strand breaks. And with dicentrics, yeah, if you're looking at the old literature, and also what is used in Bayer and ICRP reports. These are really the data from the dicentric inductions and, of course, cellular survival. But dicentric is much more sensitive to different radiation qualities.
Okay, thank you.
Okay, I think we should move on.